Welcome back. Last week of class. It's been a long semester, hasn't it? Hey, but we've been on our roll. Fairly decent weather. No snow anymore, at least. So that's always a positive. Couple announcements to start off, and then we'll jump into lecture today. First is I'm not going to have office hours next week due to another thing at my kid's school. But if you need to talk to me, you know where to find me. Send me an email. We can find a time to talk. Also, I sent out an announcement today of 20 questions that I'm going to use to draw from for the final. If you want to try to focus on those, please do. Try to study if you'd like. Um, I'm going to ask you like one, maybe two, and then possibly a follow-up. So um, I hope that's enough preparation. Do you think you feel prepared? Do you feel like I've got a rubric, I've got questions, like nothing is, there's going to be no surprises here. All right? Okay. Sound good? I don't want anybody being nervous. That's the main thing. Nerves get in the way of actual. I don't know about you, but I get all nervous on those things, and I don't like doing that. So I'm trying to make it as clear and transparent as possible, so you don't have any worry about what will happen throughout. Okay? Any questions on final? Yeah. Yeah. Correct. Yes. Right. Right. Technically, and actually, I think I probably need to append what I said. It's not true. I think you could have MCMC without Bayesian. And the way I say that is the mice method is a Markov chain. We could call it Markov chain Monte Carlo. It's a Markov chain, meaning that each missing data point is filled in, and those filled in points that help in part determine what comes next, so like state of each value. And mice, I think by default, does not use Bayesian methods, does not use MCMC per iteration to estimate model parameters. So I guess I could amend what I said about MCMC, but MCMC itself is literally just a what a Markov chain is that you have a bunch of parameters, or in this case, missing data, and those parameters are allowed to stay or change the status at every iteration. That's a Markov process, right? It's just sort of there's a stochastic probability that they change, or they change a bit, change a lot. That's the technical definition of a Markov chain. Monte Carlo is the idea of simulation with the Markov chain. I think oftentimes we just omit it. So technically, any situation where you have the chance of parameters changing state from every iteration, and then the next iteration depends on the parameter states from the previous before. That's a Markov process, Markov chain. So that's the big picture. A Gibbs sampling is definitely a Markov chain, right? Because every iteration, you're drawing values from a posterior. Those values are then used in the next iteration to help figure out the next posterior and so forth, right? Same with Metropolis Hastings, same with Hamiltonian Monte Carlo or hybrid Monte Carlo. So each of the named algorithms that we talked about in Bayes, Gibbs, Metropolis Hastings, Hamiltonian, those are all versions of Bayesian estimation using Markov chains. Does that help answer your question? Hmm. Hmm. Yeah, I mean, like so the mice procedure, the chained equations. Um, it's a loose algorithm, right? You just sort of predict you're taking each outcome that has missing data and using it as a predictor or an outcome and being predicted by everything else. It's not really an algorithm to it. It's just that. So that would be a case of a Markov process or a Markov chain that didn't really have an algorithm name, right? But again, it's somewhat conflating what Bayesian Markov chain Monte Carlo is to just regular Markov processes. So does that help? Great. Anybody else? No. All right. I realize my nope, that's not. All right. Well, I'll have to wait till next break. I have like transparent or like noise canceling in one ear, which is the weirdest feeling. But evidently the audio works better. So I'll just keep doing it. I'll half hear you, okay? It's funny because I'm noise canceling my own voice, which except for within the inside of my ear where I hear it, which is an odd feeling. All right. Um, so today I wanted to talk a little bit about missing data and test scores or psychometric data, right? Um, Throughout our class, we've had a whole lot of missing data that were not necessarily test scores, but you think about a test score itself, we didn't actually observe it. So some of the things that we've learned in class are still going to apply to test scores as well too. So we'll go a little bit over what scores are, and then sort of how we use them in multiple analyses themselves. And why I say that is, how many of you are using any type of data that has some type of survey or psychometric instrument to it? Everybody almost, right? No problem. Who uses, let's see, how many of you do anything except for output the score in your analysis? Anybody? Right, Lingo does, I think. You have a model around it, or do you output the score? So what I mean by that is, what's a score, right? A lot of times we start with, oh, just add up the items. I'm going to show you that that actually implies a model. You probably already heard me talk about it and keep talking about it. I showed one of the slides at NCME this year as a discussant where they were talking about problems with some scores in a mixture model context, and I'll give you that. And as I showed the slide, people in the audience start taking out their phone and start taking pictures of the slide. And I'm like, this is not novel information, but we treat this score as if it is this piece of data that is observed. And yeah, maybe that's it. But it's not exactly that case when you start to assume that that score has some psychometric properties. And that's where the difference starts to break down. So I want to try to talk about that a little bit more today. But yeah, I mean, what I'm going to say today is probably going to make you think all the analyses you've ever done with a test score or a survey score or a Likert items are incorrect. And I wouldn't say they're necessarily incorrect, but they're sort of need some help with it. All right. So what I'm hoping you'll get out of this today is when everybody says, "Oh, just take the score," whether it's add up the items, output a factor score, output a theta or an ability estimate, what to do when you do that. Because there should be a little person in the back of your head, maybe a little version of me, God forbid I'm in the back of your head, that says, wait a minute, score's got error to it. What am I going to do with that? Right? All right. So that's where I threw this in. I gave a couple papers on the implementation of it. Today's lecture is more along the 1992 paper by Bob Mislevy and colleagues that talked about plausible values, the use of plausible values in test scores. Now remember, that's 1992. That's a very long time ago, like 33 years ago. So computing was not quite the same. So I think in the paper they're using 4 or 5 plausible values. That's like us when we talk about imputation, 4 or 5 imputations, like Rubin's not late 80s stuff as 4 or 5. We've gotten better, at least in 30 years on computing. Maybe not philosophically or an implementation of this idea, but for computing, we've gotten better. Anyway, all right. So overall, the purpose of this class, the main message of missing data is that multivariate analyses with and without measurement error should be conducted simultaneously. And if not, we should go with a process that sort of mirrors that simultaneous approach. What do I mean by that? Simultaneous analysis. That's the maximum likelihood approach we're talking about. How we did missing data with maximum likelihood. Not always the case you can do that. Right? So we flipped to Bayes. We saw Bayes plus auxiliary variables threw everything off. Then we flipped to multiple imputation. Multiple imputation was effectively trying to mirror what maximum likelihood did by filling in data points, running multiple analyses, and aggregating those results, right? So as you know, that's that last bullet. We cannot always do a simultaneous analysis. So let's talk a little bit about the sum score. Um, Sum score, meaning you give a survey out or a test, or in my case, a homework, and you write down how much each person got for each item. Correct or incorrect is a 1 0 sometimes. Likert could be an ordered integer, right? You know what you talked about. And then you add them all together. You say, that's it. Here is the score. Seems pretty straightforward, right? Who's never done that before, by the way? Like you do that before you even think. I mean, you do that. Teachers do that in elementary school. Everybody does that, right? But the problem is, so when you're studying psychometrics, there's a whole branch of psychometrics about sum scores a bit. Sometimes we call that classical test theory. But then there's this other latent variable branch out there as well, and they're somewhat disconnected. So you'll hear people say things like, and not only disconnected, somewhat contradictory, right? So I've always heard people say things, and since I've been in my career, as a student, I'm trying to study as much as I can about each of these methods. I get out in the real world, sorry, the ivory tower, ivory silo, whatever we are here in the Midwest. I don't know. Um, and it's not quite what you learn in grad school about latent variable models, outputting scores, things like that. Here's some things I've heard. Sum scores are almost always okay. You could use a sum score for everything you want. Um, Factor scores or latent variable estimates are okay, but only if they're from some strange sounding model. Now, I say that's kind of weird. What's a strange sounding model? Anything that's not factor analysis. Why I say that. So, my first year as a tenure track faculty member, uh, way back when, we're going to have graduate admissions. And uh, just before graduate admissions, I remember this clearly, there was a seminar about, you know, factor scores or so forth. And it was in the psych department. These are not quantitative psychologists, but people who are pretty well versed in things were saying, oh, you should never use a factor score. Can't use a factor score. Factor score indeterminacy is bad. Bad, 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 bad. Don't ever use a factor score. And then in the next meeting we had, we're looking at student applications and they're looking at a GRE score. GRE scores are factor scores, right? What's the difference? Oh, factor scores. We said factor, not ability. Ability comes from item response theory. That's what it is, right? So, so long as it comes from something other than factor analysis, cool. But factor scores are like the work of the devil. I don't know. That's just put that. It's just what people would. It's like there's these long-held beliefs that are strongly entrenched, and they come from an era of where, yeah, factor scores were problematic. They're less so now, especially when you build things with a purpose. So, um, another question I keep hearing is, or I've heard is, like if you're in the structural equation model class, that's the other announcement I didn't make. I'm not teaching DCMs next fall after all. I'm sorry for those of you who wanted to take it. I'm actually going to teach SEM because of course rotations and so forth. So if anybody wants to learn the SEM approach, many of you have already taken it, right? How many? Nobody has. Yeah, yeah. None of you will probably apply. But if you haven't taken SEM yet, I get to teach it. If not, sorry, you don't want to hear DCMs anyway. Um, Anyway, so if I'm teaching structural equation modeling, I hear this. I'm going to do a structural equation model, or why use structural equation modeling? When I just sum up the items and get a score, right? Think about it. In SEM, the measurement model, you've got to map every item onto some factor usually. And then you got to check model fit. That's a pain. Oh my God, it's horrible, right? And then you got to make it fit. If it doesn't, terrible also. Um, so yeah, that's what people tend to think. So some scores are used as observe, but we use some scores all the time. Like I mentioned this. Almost everybody here has a sum score somewhere in their data. They're either observed variables in secondary analysis, that'd be your case, or we give those as results to people who give us data, right? They give us item responses, we give them the result, right? Um, so current practice seems to be we can use a sum score until some reviewer, maybe reviewer three. These are older slides. We don't have reviewer three anymore. That was a big change in my career. It's always been. It's like how many people submit to journals where you get three reviews? Anybody? I always get two now. When I started, it was all three. What happened to peer review? Anyway, never mind. The sum score until you can't use one. At that point, we use a confirmatory factor model to verify we have a one factor scale, and then we use the sum score, right? So this lecture sort of dives into that. Today, we're going to demonstrate. I have some data online. I probably won't flip to R. I'll just talk through it. These are data from a long time ago where you probably saw this if you've taken Lisa's class. These are my data. They came from me. All right, not me. I was part of the data collection activity with this. All right, but she's welcome to use them. But these are something called the Gambling Research Instrument. There are three items. the purpose is not the actual data themselves. It's sort of seeing some properties of scores. There's these three items were supposed to measure a person's interest in gambling. Maybe more borderline, um, what's the word I'm looking for? Gambling disorder, right? You know, it's almost like an impulse control. Gambling, blanking on the term now, but gambling, is it? Problem gambling is an impulse control disorder. There's the last, that's the end of my psych training there. I'm done. Okay. Um, so these are Likert items, but the same thing applies if you have binary items. In fact, binary items, very interesting. If you're adding up test scores, what I'm about to say for Likert items applies to binary. So you get an extra big benefit of now you've got to worry about link functions, all the other stuff that aren't there. So each of these three items are 1 to 6 integer unit scores, meaning a 6 is a person would endorse the item, a 1 would say I strongly disagree, 6 would strongly agree, and then various shades in between. So the sum scores themselves fell between 3 to 18. And here are the sum scores. Look at that. It looks like a staircase almost, or like a slide, maybe like a half pipe, like a skateboard ramp, something like that. Um, this is telling you what about my scale? These are items that are like, you know, I frequently think about gambling, or I've lost friendships over my gambling amount. Right? This is telling you not a lot of people had that problem, at least when these data are collected. Now, this was right about the beginning of when everything started to change about gambling rules in our country. It used to be that you couldn't just gamble everywhere. You had to like go to a place or go a long way to a place. And now it's like literally, if you wanted to right now, put a wager on tonight's basketball game, let me know what it is. No, just you can like pull your phone out and take care of it right here in class, right? So this is a little bit different when gambling is a little bit more limited access. But that's not less the point. We're not going to talk about gambling as much as we're going to talk about properties of the sum score. Um, so the use of sum scores brings about discussion about the use of psychometrics or the psychometrics that underlie their use. You've probably learned about classical test theory, writing items, building scales, item analysis, score interpretation, and evaluating reliability and construct validity. Those are the features of it. But for us, the big picture is we're going to view classical test theory as a model, an actual model, with a restrictive set of assumptions within a more general family of latent trait measurement models, right? So we can actually embed the sum score process in a method that mirrors it. And if we work really hard, we can actually get the sum score back from the method. If we work not as hard, we can get something that correlates a value of 1 with the sum score. So it's a scaling issue. So we're going to use confirmatory factor analysis for this. Factor analysis. I didn't talk a lot about factor analysis in this class, even though we used the SEM framework. It was more the idea of multivariate analysis that came from the SEM framework. So you probably saw this slide in Lisa's class. By the way, she taught SEM. I don't know if you know, did she ever tell you the history of our SEM joint venture? So at Kansas, we cross-listed that class, and she would teach it, and I would teach it in our just different departments every year. So we developed a lot of those slides together, although this lecture came before that. She didn't want to incorporate this in her slides. Where we started talking about this is when she was first year in faculty in 2006, long time ago. And I was teaching an intro measurement class with Rod McDonald's book in 2006. So some of these slides date way back to all that. And this is one of those right there, right? Um, so what is the name of a latent trait measured by a test? This is part of the issue with the idea of a score, right? The classical test theory, we're looking for the true score. Confirmatory factor analysis, we call it the factor score. IRT, we call it theta or ability. It's okay. Countdown. This is the final countdown. If you could just play that song next, I'll be okay with it. All right, no problem. Um, the fundamental difference in the approach, it doesn't matter what you call it, but if you think about when we talk about classical test theory, items are thought to be exchangeable, meaning it doesn't matter what the item is, more or less. It's the total score that matters, right? Whereas in all of the other measurement models, we have item level models themselves. We have things called item parameters, right? We have a model for each potential item itself. And so this latter model seems to be a lot more flexible because items don't all contribute the same to the score potentially. And that seems to fit data much, much better. So in classical test theory, the test is the unit of the analysis, right? So we have a total score is equal to true score plus error. The true score is your best estimate of the latent trait, or another way of putting it, you've all know this, right? Many of you know this. If we had infinite replications of this assessment, the true score would be the mean over this infinite replication, right? Somehow we wipe the brain clean after every time. Also, there's error, right? So expected value of 0 for error, it's expected to be uncorrelated with the true score. So therefore, after these infinite observations, error goes away. Also, I will note that this is, people argue about whether this is a model or not. But to me, if you have an equation, it's a freaking model. So I'm just going to say it's a model. That's my take on it. Do you believe it's a model? Sorry, I just put my. Who wants to argue? Let's go. That's what I feel like I just did. I believe it's an argue. I said that forcefully. Hey, do you? No, that was a loaded question. Anybody want to debate that? Let me put it more academically. I'm willing to be wrong, but I think of it as a model. We good with that? Okay. So the expected value over these infinite replications of y is the true score. Um, so put another way, should the model fit? Y, the total score, the sum score, is an unbiased estimate of your true score. And the true score is why you created the sum score in the first place. Your test purports to measure one thing, bringing about one sum score per person, right? With this, we have no distributional assumptions on y or t or e. It's just simple. And even if your data fit a one-factor model, when using a sum score, the error portion actually becomes part of y total, right? But it's only one part of the error that's in a sum score. So again, let's back up for a second. A sum score, adding up items. In other parts of statistics, we call that a linear transformation, right? Or a created variable, right? We create a new variable through a linear combination of a bunch of other ones. You see this all the time. Principal components, adding things up. And you don't have all this other baggage that I'm talking about here. Why is that the case? It's the case because if we just added up all our stuff and it represented some aggregate itself without a model behind it, it would be, we know the properties of that aggregate, right? We could describe its variance, we could describe its mean, we could describe how it relates to things. And what we're trying to believe is that each one of those things that we added up are measured without error. It's only when we start to assume this, that the sum score really is a or a combination of a true score plus some error, that then now we think of it as now it's an estimate, right? Even though we can observe it because we added up all these items, if we want to believe, wow, that's part of a true score, that puts it a little bit differently, right? Now we describe it, we have to think about how much error there might be in the score. Even though your score is a 12, if the test's reliability is 0.6, your score, that was just this version of your score. If we were to do this infinite process, your score would range quite a bit, right? So this is the disconnect in some scores, the observed data versus the psychometric quantity. And for us, for what we're doing, most likely it's psychometrics. Why is that? Each item response is not measured perfectly if you believe in this type of theory. Even though this doesn't reach items, the other factor analysis in IRT does. When you believe that the sum score represents some type of estimate of a true score, implicit to that is that each item measures not only the true score, but also some error along with it as well, too. And that is different than when you sum up things with no error. Does that make sense? Right, if you take things with no error, add them together, you get a new variable with no error that has properties that are well known. No problem. It's only when you want to believe this is a sample from a universe where a person has this latent trait that you start getting out of that framework. Make sense? Cool. Okay, so because classical test theory does not include individual items, the items themselves are assumed to be exchangeable, meaning that it doesn't matter what the items are, how you get better reliability is you have more of them. Always more. More is better. Sounds like sample size, right? By the way, your answer should always, someone that says, how big of a sample size do I need? The answer should always be more. Always. Am I right? even if that's not possible, like we talked about, I think last time, like the infinite effect size, right? All right. So the goal of classical test theory is really to put some type of understanding of how much error there is in the test. We can talk about reliability as a function of this. Reliability is the amount of how sort of the correlation between y total and the true score, the squared correlation between it. Um, this is so here the reliability that you've probably seen these decompositions of reliability. We could use this. I taught this in this class. The variance of y. Remember variance? Remember those algebra of expectations way back in the day, like back when it was snowing and cold and less miserable, more miserable. Excuse me, more miserable. This is less miserable, right? Maybe you like the cold, but sorry. Here I am giving you strong opinions. This is a model, and it's miserable when it snows. Yes, the end. Um, Jonathan let loose at the last day of class. Excuse me. At least it's opinions about benign things, not controversial topics, I think. Anyway, I said, so the variance itself, we can talk about from classical test theory. The variance of total is really the variance of true score plus error, which is the sum of each of the variances plus 2 times the covariance. And this is where the convenient feature of not having a correlation between true score and error comes in. We can set that covariance equal to 0, meaning that the total variance is really a sum of the variance of true score plus the variance of error. When we get that, we get to our reliability or classical reliability formula in this case, which is reliability is the variance of true score over the variance of the total score. Put another way, the variance of true score over the variance of true score plus error. Right? So that sounds great. And if you were like me when I was taking my first class on this topic with Rod McDonald way back when, I was like, yeah, but I only have Y. How do I get T and E, right? Well, that's where all of the methods of quantifying reliability was. But this is basically Spearman's 1904 idea of disentangling quantifying reliability, right? So let me talk about one other caveat of sum scores. There is a tendency in different fields to use something called item parceling or item bundling. I don't know if you've heard that before. Basically, the idea is you take a bunch of items, make a sum score out of them, and then put that sum score in another model, right? That is still um, uh, doing the same process. You're still making a sum score. Parceling itself still has that. Parceling, let me put it this way, parceling is frequently done to hide model misfit. Let's just put it that way. If you parcel, what I'm about to tell you, you should build a model for the parcel itself with the assumptions built in from classical test theory and fit the whole model itself. You'll see it probably never doesn't fit. But if you add things up and then correlate the things you added up or put that in the model, that fits usually well. And the reason for that to me, a lot of time comes down to, remember model fit. We talked a little bit about model fit methods, RMSEA, CFI, TLI, a little bit in this class when we got into the multivariate designs. Those still stay with us here. They're based on your model implied covariance matrix. And if you think about, let's imagine I had a model with 20 items, but I decided for whatever reason that I'm going to sum up the first 10 items and make a sum score out of it. And then I'm going to put that sum score with the other 10 items in a model. My covariance matrix for the original model would have been 20 by 20. For my new model, it's 11 by 11. It's a whole lot fewer cells that a model has to adapt to, a whole lot fewer places where you have to fit to, right? So it's almost a numbers game. You have far fewer degrees of freedom when you bundle or when you parcel or when you sum things up and stick those in a model as well too. So what are the potential sources of error in a sum score though, right? Clearly, measurement error. We put that in the model. There's E there, right? But there's other misspecification error of various types. We could have dimensionality specification error, right? So when we assume all the items measure the same thing and we add them up to make one score, if they don't measure the same thing, that's going to be wrong. That score is not going to be accurate. If they measure two things, for instance, right? Another part is, and we'll see this a little bit more in just a bit, there is what we're going to find is that sum score itself follows a parallel items model. And parallel items model a confirmatory factor model where each of the loadings is constrained to be equal across items. Each of the unique variances is constrained to be equal. And that's a testable hypothesis number one. But number two, it's unlikely to fully fit exactly in your data. So there might be misspecification on parameter constraints, right? Another misspecification error is the case where, let's say we add up a bunch of binary items, right? Um, actually, check that. Let me back up here. That's down here. Linear model functional error. If there's not a linear relationship between the items and the factors, you're going to have a problem there. It's hard to tell in classical test theory. Um, if the other part of the sum score is all of this, once we start getting into error distributions and so forth, is taking discrete data, summing them together, and pretending it's continuous is also a source of error because that discrete data, Likert or binary responses themselves, would normally have some type of link function or something else that describe what it does. Otherwise, distributional specifications get a little weird. So that's another place of error. And the other thing we can get is something called factor distribution misspecification error. So you might assume in certain times you make assumptions about the distribution of a trait itself, and it may not be right either. But anyway, the other part that we could find here is missing data error. Now, you know about missing data error. You've seen that in this class. Can you imagine what you do? Could you imagine a 10-item survey and you've got missing data in it? If you just give the, let's say, average response, so you take the sum for each person divided by the number of items they responded to. We talked about that in the beginning part of class. That makes assumptions about missing data that we don't like to make. Now, with all of your skills in missing data, we really can't use maximum likelihood for a sum score. Can't use Bayes for a sum score. Could use imputation, right? So you can imagine doing multiple imputation for the missing data and then having it produce a sum score. But missing data itself could also be an error if you don't end up doing that. Right? And then sampling error is not really an error in the sum score, mainly because we don't really have a lot of parameters in this model. So it's not all that bad. In bigger, heavily multidimensional, complex psychometric models, yeah, sampling error could be a big problem. Point estimates, the parameters could have very wide distributions, uncertainty in a lot of those estimates. And that could underestimate your uncertainty in the trait, but not here. Any questions so far? I'm just spewing. All right. So ignoring error, we saw this in missing data. What happens if we ignore the potential error from missing data? Everything could be biased, right? Everything from the point estimates to the standard errors. Like in the best case scenario, the standard errors are, the point estimates are fine. The worst case scenario, everything is bad, right? The same thing happens here if we think of ignoring each of those errors from a sum score as well. So I'm trying to map and commingle what we've talked about from missing data with what we think about with error in a psychometric sense. Okay? Some source of error matter more than others. So not all these types of error are the most damaging, right? I would say that dimensionality misspecification is probably the biggest because that's, if you have 10 items measuring one thing and really there's 5 with one dimension, 5 with another, you have an indirect measure of the dimension you were after, right? Measurement, so there we go. Measurement error is thought of as the worst. Actually, model misspecification, I just contradicted myself here. Pretty funny. I should read the slide first before I give it. Model misspecification error, this is the 5 types of error here, is really worse than measurement error. So that's actually it. If you were to go chunk all these together, we know measurement error. But if our process is approximately correct, measurement error will affect our accuracy. We'll think we're more accurate than we really are if we don't account for it. But it may not affect the bias. All of this stuff right here are things that with a parametric model we can assess more frequently. This chunk right here is the worst. And embedded in that, of this chunk, I think dimensionality is probably the highest. How's that sound? There's some consistency in my explanation. Okay. All right. Here's an example. My GRE scores. This is a slide Lisa built way back when, also when we were in the psychology department. In the psychology, the story I told you about, factor scores are terrible. Now show me that GRE score was there, right? This is the error bars. This is the original GRE score guide between 200 and 800. It's changed now, but you can try to. Good luck finding this, by the way. I don't even know if ETS is publishing this anymore. And I heard a report from the. Well, I'll just leave that off right now. I know they're not publishing validity evidence anymore. So my argument about GRE was really nice back in the 90s, late 90s, early 2000s. Really nice theoretical testing program. Suffered from not describing this fully. One of their motivations of changing scale scores to the new score format, where it was like 130 to 180, was to make a point that two scores, like a 130 and a 131, are really indistinguishable from each other, right? So you can't go and do that. You can't go and compare people based on their scores unless they're far apart. This is error bars, 95% confidence intervals around the GRE itself. And the thing I want to point out to you here is I love this middle of the range here. 500 was right about where the mean was. If you scored right about the mean on the test, you were somewhere between 400 and 600. Right? The scale went from 200 to 800. So you paid ETS for the pleasure of taking half the scale and saying, I'm somewhere in the middle half. That's great. Right? And showing this to people and describing this to people about GRE was hard, especially in educational measurement programs. Let me tell you, there are places that revere the GRE because that's what we do. And my argument's always been, if that's what we do as a science, we should evaluate it like we do here and not with marketing. And so that's been a big problem. But on that note, there's a lot of error in scores. A lot. It happens. But like right here. So, all right. How are we doing? There's a point to all this, I promised. Let's go with factor scores for a bit. I'll start with the CFA model. Remember the CFA model? For a given item response from a person, so person P, item I, the model has an item intercept plus a loading for an item times a factor score plus error. In a different context, we would call this simple linear regression. Had we observed the factor score, this is a regression model. No more, no less. Right? So a factor score is an estimated value for F. Sometimes we'll call that F hat, just to, got to put a hat in there somewhere, right? I don't know. It sounds statistical that way. And again, there has been this long resistance to using factor scores in psychological research, with the most common objective being this indeterminacy of factor scores, which is the idea that for a given solution or a given set of estimates, the factor scores themselves are not unique. Meaning, and this is where if you took exploratory factor analysis, the third about exploratory factor analysis, rotation of factor scores, right? Well, why are they not unique? Because factor models have to fix some parameters for identification. This is another way. So, for instance, if I have a CFA model, I could use a method of identification where I take the factor, I assume its mean is 0, its standard deviation is 1. And if Erica has this same model and she says, no, I want to estimate the factor variance, I'm going to fix one of the loadings to 1, the marker item approach. The scores that we would get out will be different, right? They're on a different metric. Now they're correlated with the value of 1, right? You can transform one to the other perfectly, but that's part of the issue people have. And even before that, before we get into that, back before we had a whole lot of maximum likelihood versions of factor analysis, we would have to use approximations to factor models. Basically, anything involving principal components or spectral decompositions of matrices fall into this camp. Alpha factor analysis, image factor analysis. And what you would end up doing is estimating a whole bunch of things and then rotating them to try to see if you can make understanding for it, right? The rotation itself was not supposed to change the result. And in most cases, it wouldn't. You'd have the same, it's just a reconfiguration, a change of basis, a change of space to see your result. And that's where the bad idea came from, which is if I have a result for these factor scores, I look at them this way. And if Erica takes my result and says, no, I need to do a Varimax rotation to it, C looks at them a different way, and we're going to have different numbers, and different people are going to be different higher. But for all the confirmatory methods since the late 1960s, we don't rotate anymore. We define the factor. And that's where indeterminacy is less of a problem, right? We say these items measure this factor. We test its model fit. If it fits, it's fine. We could still rotate it, but why would we? We've already defined what that factor is rather than have to explore what it happens to be. Make sense? All right. Here are example factor scores and their distributions. So a factor score itself doesn't exist. You can get a program to estimate one for you, but what it's actually trying to estimate, and I'm going to use a Bayesian version of this. If you don't want to do Bayesian, you can think about this as an asymptotic distribution from maximum likelihood, meaning assuming you have enough items where the distribution becomes normal, each person's factor score is at the middle of their distribution. So here's 4 scores on on that gambling tendency scale itself. What we would normally describe for each person is sort of the center point, right? These scores, I can tell you, are all normally distributed because they came from confirmatory factor analysis. So the mean, the median, the mode are all equal. We know in Bayesian statistics that's not always the case with posterior distributions, right? More on that in just a minute. But here, each person's score is in the center of the distribution, and there is considerable overlap of people, right? So this gambling tendency factor score right here, scale, I believe the mean was at 0. Let's just say the mean's at 0 and the standard deviation might be estimated here. I don't know the standard deviation, but you can see here, take a look at this person in the blue. Their factor score is like a 2.25. The person in the black, their factor score is like 1.75. Sorry, 2.25.75, right? So you'd say 2.25 is a lot higher than 0.75. They must be different, right? Maybe, but there's an overlap in their distributions. What's that tell you? There's some non-zero chance the person at 0.75 has a bigger score than the person at 2.25, right? So that score, having that error, is important. I'm trying to establish there's error in these scores. You don't get away from it. And the same problem with not observing data and missing data is what we're going to have here with factor scores. So what I'm getting to is factor scores are giving you a weak ordering of people. What's a weak order? You're saying that there may be another person who's way out here that their distributions overlap only in the infinitesimally small part of the tail, right? So you'd say they're close to 0 chance that they're bigger than the other. That's a strong ordering, right? That means the person that we didn't observe, the planet 9, planet X. I hear we're going to observe planet X pretty soon. Did you hear this? You know what I'm talking about? There's a planet that we can't, that people are speculating exists beyond Neptune, and people are trying to pin it down. And then there's a new observatory supposed to go online later this year, and we're going to find it. All right. So anyway, that's that person out here, Planet X. All right. We would definitely be say that they have more of the trait than this person with the black distribution. Right. But for most of it, we'd say, yeah, the blue distribution is higher than the black distribution, but there's a chance it may not be. It's like a fuzzy ordering. We most likely think that's the case, but it's not guaranteed. That's what a weak order is, where we can order some individuals, but not all, right? And the purpose of measurement, purpose of factor analysis, classical test learning, everything, is to take observed behavior, usually in the form of responses to surveys or tests or questionnaires, and map that onto a continuum where people are in order, right? So when you hear that, and people ask you, what's the nature of theta? Is it and what type of variable is it? Is it interval level? Is it ratio, nominal, whatever? That's where you have to think. Is it? I don't know. It's got error to it. And there's actually quite a bit of error, like the GRE had. A surprising amount of error for what we use tests for. So that's where I'm going with this. Factor scores are distributions of some sort. So these factor scores are found using the same methods that are used in practice for finding test scores like the GRE. And the only difference with what I just showed you is the distributional assumption. The GRE assumes scores still normally distributed, but the items themselves are Bernoulli distributed, right? Whereas CFA says the items are continuous. those just because the distribution doesn't changes doesn't mean that the score properties change. We saw that in this class, particularly when we had a piece of missing data that might be Bernoulli. We had to change the distribution function to impute it or to build it or to put it into an analysis correctly. But the theory and the process didn't change, right? So I found this to be fun too. A long time ago, um, this was a response. One of the professors at UT Austin, a professor at UT Austin named Walter Stroop, sort of did not like how Pearson was administering accountability exams and tests in Texas. And it led to this really interesting academic versus industry divide, particularly because Pearson had to contribute a lot of money to UT Austin's measurement program, endowed a professorship. There were lawsuits and so forth. But I found this is a response from Pearson. IRT does not rank order students or select test questions. IRT measures students' academic knowledge and skills on a scale like a ruler. Ruler has something that IRT doesn't, though, right? Ruler is measuring length. There's a fixed 0 point for length. We don't have a fixed zero when we think psychometrics. Anyway, and just like a child gets taller, when students increase their knowledge and skills, their test scores will increase. IRT provides a thorough and fair measurement of growth and mastery. I love all this statement. I would pick that thing apart. Does IRT not rank order students? Wouldn't you say if the scores were the center of this distribution, that's a rank ordering? Does IRT follow a ratio? Does the theta estimate follow a ratio scale? No. And this is my problem with a lot of, I will just put it out there, industry people, is that you're learning science here. And the more that they don't map onto science and what they do in their business practices, it slows us as a science down beyond that. So I looked at that and I thought, I got to point that out. I don't think the link works anymore, but that was a pretty big deal like 2015, 10 years ago. It was pretty fun, very interesting to me see all this happening. Like, exactly. Anyway, all right. So let's talk a little bit more about that. Any questions about this I should ask? And keep throwing it at you. Factor scores themselves, or the process of what we're doing, but they go by their names, are actually used in other domains. Okay? So it's not just psychometrics. Bless you. Because the historical relationship between confirmatory and exploratory factor analysis, I mentioned factor scores are widely avoided, right? There's rotational indeterminacy issues in EFA. Uh, Similarly, factor analysis has been around for 120 years now, at least. Thinking of Pearson being kind of Spearman's other 1904 paper being sort of the beginning of it. So along that time, people came up with many, many different methods to estimate factor scores. You can find an example. If that link still works. I don't know if that's been purged by the government yet. So, we're going to focus on only one method for estimating factor scores. It's used in nearly all fields, and it's based on the posterior distribution of the factor score given the data. If you don't like that, you could think of maximum likelihood and assuming a limiting distribution alternatively. This method is identical to methods. There's a great technical factor analysis book from 1971 by Lawley and Maxwell. By the way, that book will tell you the secret why EFA, there is no such thing as exploratory factor analysis in likelihood-based measurement. So go read that. And then way back to Bartlett scores from 1936. This is also used, this method that I'm talking about here, if you go and use a mixed model, multi-level model, longitudinal model. You have to keep going, all right? If you're using Proc mixed or LME4 or whatever to estimate your multi-level or mixed model, and you wanted to go and actually get an estimate of each person's, let's say, random intercept or random slope, the process I'm going to tell you for factor analysis, if you're using normal theory for that, is the same. And in statistics, people will call those estimates best linear unbiased predictors, or BLUPs. And if you really want to get into a stat argument, that's comparison to the fixed effect estimates, which are called best linear unbiased estimates, right? So at that note, I'm going to pause for a moment, a big picture. Let's take 10 minutes and we'll have a break and I'll come back and throw more at you. Sound good? All right, let's talk factor scores in the big picture. Um, The factor score itself is the estimate of the subject's unknown, unobserved latent trait. You know that. We put it in the model, right? Um, because this latent variable is not measured directly, it's like missing data. You really can't know what with certainty its true value. So there's your connection. Ta-da! It's a little bit different in some ways though, because the factor score, we have to construct what that is, right? We have to build a measurement model and we have to evaluate that measurement model, and then we might be able to use that factor score. Whereas in missing data, most of the time we don't build a model, it's just missing, right? We have to figure out all the ways that it could be missing or figure out what might relate to how it's missing. So in some ways, having a factor score look like missing data is easier because we have a better sense of what its properties happen to be. It's certainly not going to be missing at random entirely, potentially missing completely at random. And I think why I said entirely for missing at random, I hesitate on that because if this factor score comes from variables with missing data, observation with missing data, then perhaps missing at random would apply to the factor score as well too. So it's sort of somewhere in between. How's that sound? So because it's difficult to pin down what the missing value happens to be precisely, right? It is difficult. Excuse me. We saw the distributions, those posterior distributions of factor scores. Often the mean of the posterior distribution of the fact is given as the score, right? Here's your score, your point estimate. I say often, but we know in this class, or we know from Bayesian in this class, we summarize a posterior distribution with multiple ways, right? There's the EAP estimate, which is its mean, and then there's potentially an MAP estimate, which is its mode. And in the case of factor scores from a confirmatory factor analysis, the mean and the mode are identical. In item response theory, they're not guaranteed to be, but as the number of items approach infinity, asymptotic convergence happens, meaning the factor score distribution converges in distribution to a normal distribution, which should give the same mean and mode. But this is why, in some cases, the choice of which factor score you're using in terms of estimate for the posterior distribution matters as well too. But depending on the test, as we just saw, there could be a lot of error in the score. Like again, in 2011, if you wanted to pay $300 to ETS, you could figure out if you're in the center of the distribution. Basically, you could trim that distribution from 200 to 800 to 400 to 600. I guess that's the center 200 points of the distribution. Not half, I guess it's a third. Third? Yeah, a third, right? Yeah, a third of it. Now I'm in the center third of the distribution. I misspoke the last time. I apologize. Um, Therefore, to me, to use factor scores, we have to reflect on the fact that the score is not known as represented by a distribution. Where have you heard that before? That's like this whole class, right? So what did we use when that was the case in missing data, if we wanted to assume missing at random processes? Simultaneous analysis with maximum likelihood. You know what we call that with factor scores? A structural equation model, right? Bayesian. Well, we can do a structural equation model in Bayesian as well too, where we simultaneously estimate the factor score, but then have it either be predicted or predict other things. The structural model in the structural equation model. And what was the last way? Multiple imputation. That's what we call plausible values. So literally the same idea about factor scores still exists that we talk about in missing data. It's just with factor scores, these ideas have been around a bit longer, right? Structural equation modeling came around 1970s, Lizerol linear structural relations, et cetera. Early 70s, late 60s, Skog's 67 paper about maximum likelihood factor analysis. Like, read that one, that's a classic. That led rise to the ML methods. And as soon as we learned how to do Bayesian, we could map the ML methods onto Bayesian as well too. But the 1992 paper I shared with you is really the plausible values. That's multiple imputation, effectively. All right. So what I'm trying to make the connection for you with is all the things that we talked about with missing data apply to your factor scores or your sum scores. And I'll show the connection between factors and sum scores in just a moment here. And if you're not doing that, you can imagine what might be happening to your analyses where you use that. Okay. All right. So there's our weak ordering. This is a comparison of distributions. By the way, this is the CFA case on the left here. And I'm going to derive the factor scores quickly, just because I wanted to do that. Under CFA, we'll show they're normal. When they're not quite normal, you could have a distribution that looks skewed. I tend to say that in my experience, like if you run a Bayesian algorithm take a 3-item item response model, like something you probably wouldn't do in practice. Look at the posterior distribution. It's not quite skewed. It's more like platy or leptokurtic, like it's too heavy in the tails or too thin in the tails. I wouldn't say it's necessarily that, which means the difference between MAP and EAP is less, even if it's so long as it's symmetric. So I wouldn't say it's as exaggerated as that, but that's just a point to make, right? The EAP estimate is pulled toward the tail because the mean is subject to is somewhat of a not so robust measure of central tendency, whereas the mode is the maximum right here. Right. All right. Turns out there are different ways of computing standard errors for each, right? So the factor score distribution for EAP factor scores, the mean, the point estimate is the mean of the posterior distribution, and the standard error is the square root of the variance of the posterior distribution. And for MAP factor scores, the point estimate is the maximum of the posterior distribution. And then the standard error we find by Fisher's information. So interestingly, when we talk about that, this is a weird disconnect you don't see a lot. It took me a long time to learn this because you read about IRT in the IRT context, usually from an ed measurement group, and it's somewhat narrow focused. Let's put it that way. It's how we do things in ed measurement. Well, never minding the fact that all this stuff didn't get invented in ed measurement, but we borrowed, right? And so what you learn about is, oh, what's the standard? What's the condition? How do we find our conditional standard error of measurement in IRT for a theta? We use Fisher's information. Well, that's the case when we use either maximum likelihood or MAP for theta. Oh, and by the way, that posterior distribution, if you're using Fisher's information, also needs the distribution assumption if it's Bayesian as well, too, for MAP. You don't see that in a lot of books as well, right? So the disconnect between the two, if you're wondering when I use Fisher's information or when do I just take a variance of the posterior distribution, Fisher information is at the maximum. It's the curvature of the posterior distribution at its maximum. This is the variance of the posterior distribution, right? So do you see that? Anyway, another added on feature of weirdest. This is me ripping on like how we teach psychometrics. It's not unified as much as we need it to be, right? All right. So for CFA measurement models, I mentioned the MAP is equal and the variance is identical regardless of source. And for variance is identical. So in CFA, we can show that the point estimate of the factor score is unrelated to its standard error, meaning if everybody took the same items and there was no missing data, regardless of what your score is, everybody has the same error, which is why in that plot of the 4 distributions, they all the same width. It was a CFA result. In non-CFA measurement models, the most predominant, at least that I talk about, is item response theory. We know that the MAP and EAP is not necessarily equal, although as number of items go up, they converge. And the standard error is a function of the factor score. That's why we call it the conditional standard error of measurement, right? And that stems from the fact that in CFA, all of the items are assumed to follow a normal distribution, which is implausible, but that's what we do. So distributional quirk. But we can tie factor scores to classical test theory, right? So here's our classical test theory model and a reliability for it. If we think about the quantities that we get from the factor scores, we can actually map on true score and error to the factor scores themselves, right? The variance of true score, well, that's the variance of our factor. We can truly estimate that. Sometimes we set it. We say it has to be one. It's an identification condition. The variance of error then comes from the squared standard deviation or standard error of the factor score itself, right? So we could actually compute a reliability of factor score using model estimated parameters. So that's the first thing I want to talk to you about. When we talk about reliability estimates, we can show that, and I'm going to show this in a couple slides, our parameters of our model will give us equal reliability estimates that we would find if we were doing classical test theory. Spearman-Brown, alpha, or sometimes people call omega the congeneric version of it. Each of those can come from model parameters. So therefore, reliability, if it depends on model parameters, reliability, an estimate of it, cannot be used as model fit, right? And in classical test theory, some people say that, oh yeah, I added up all my items, reliability is 0.92, that's great. Why can it not be used as an index? We can't use it for model fit? Because if your model doesn't fit the data, your parameters are biased. So for reliability estimates, whether they're any of them, classical reliability or otherwise, to be estimated to be true, your model must fit your data. If it doesn't, this is likely an overestimate, almost always. I've never seen it be an underestimate. So what I'm saying about that is don't ever say reliability is model fit, but also connecting reliability to parameters of the model itself. All right. The empirical, most, if not all, latent variable techniques, for most of them, they factor scores come from empirical Bayes. It's not always the case, I should say. Empirical Bayes is used in a lot of places that aren't the testing industry. In the testing industry, we use a lot of maximum likelihood estimation for um, the factor score itself, or we do some type of conversion where we move the factor score onto the true score metric through a test characteristic curve. But I'm going to talk about empirical Bayes here. The other stuff, I think what I'm saying certainly applies when it comes to error, but just determining what error is a little bit harder. Um, so here, empirical really means some or all of the parameters of the distribution are estimated. In our case, the factor, mean, and variance. And Bayes comes from the use of the term Bayes theorem. Now, I will say empirical Bayes is the stat term for it. The BLUP, B-L-U-P, is called an empirical Bayes estimate. And because of where it comes from in mixed models is often part of the prior distribution is estimated. If you think about a model with a random intercept, the intercept variance is estimated as part of the model. That makes it an empirical Bayes estimate, or sometimes we would call it an empirical prior, right? You've heard that term before, heard me use it? So that's where it says empirical Bayes. Empirical Bayes kind of breaks down in the case where we have a factor model and we identify the factor, mean, and factor by saying the mean is 0, the variance is 1. There's nothing being estimated there. But that term I'm borrowing from statistics to kind of show the connection between what we do. So this is true for all CFA models, IRT models, hierarchical multi-level mixed models, and any measurement model that doesn't have a name. You have a Poisson count variable, put that in the model too. Cauchy variable, I don't know why you would, but sure, put it in the model as well too, right? Anyway, so we saw Bayes' theorem before, right? The distribution of A given B is equal to the distribution of B given A times the distribution of A over the distribution of B. Here, in this sense, the distribution of A by itself is what we call the prior distribution. The distribution of B given A is our model data likelihood, is what I call it. It's our model, right? And we put it all together and we get this posterior distribution. Here we can do the same thing with the factor itself. What we're really after is the distribution of the set of factor scores conditional on the observations of the response data they gave. We can do Bayes' theorem on that. That's equal to the distribution of the data given the factor. What I'm going to show you is under the CFA model right there. That is multivariate normal times the prior distribution of the factors, also multivariate normal. And that's divided by the distribution of the data, the marginal distribution of the data. So here what we can say is for a single item, our measurement model is given by this regression equation, for lack of a better term. And it has some error variance, which we call unique variance in the factor analysis world, right? And then using expected values like we saw in this class, we can say that really what that means is the distribution for a single item, given the factor, is normal, where the mean of it, what Lisa would call the model for the means, provides the mean, and the variance is the unique variance itself. Yes. Mhm. So here, right here, you mean? Oh, right here. Yes. So what I'm building is the first part of the numerator in Bayes' theorem, the model data likelihood. So that's always the case, right? The data, we always have a distribution for data in Bayesian, and that's a core part. So whenever we use Bayes' theorem, that's a core part of what we derive. I don't know if I fully answer. Mm-hmm. But, yes. Okay. Yes. Yes. I think I understand now. Yeah, so that's because we're Bayesian, and that's the Bayesian label for it. So in a maximum likelihood sense, this is something called the Bayesian flip, which is the craziest thing to me when I was learning ML and Bayes. What we call a likelihood function in ML is the likelihood of the parameters given the data. What we call the model data likelihood in Bayes is the distribution of the data given the parameters. the opposite. And people will sometimes call this the Bayesian flip. It's just a difference in terminology based on Bayes' theorem and where maximum likelihood was created, but they are the same entity. Yeah, and at some point, if you trace the math there, there's an incongruent. Like you cannot do one or the other based on mathematics unless you just acknowledge that the label is different, but the entity is the same. Okay, so yeah, sorry, good question. I'm sorry I didn't understand to begin with. Yeah, when I was really trying to understand, when I finally quit being like Bayesian, a reluctant Bayesian, and said, "Well, Bayesian's my life now." Um, I started looking at that, and that was the first place I stumbled. I'm like, my God, has it always been the same? And as soon as I realized that, I'm like, well, that now makes a lot of sense. Like, how often do you see that in different fields or different lineages within the same field? Maximum likelihood and Bayesian are estimation methods and statistics from different starting points will have different terminology for the same idea, right? Same thing with, I'm trying to cross the streams here with empirical Bayes or whatever for factor scores, right? You get this. It means the same thing. It's crazy that it does, but it does mean the same thing. Um, okay, so building this forward, this is the univariate one. If we had multiple items in one single factor, it would look like this. And I give the general case where we have multiple items and multiple factors. It's multivariate normal, right? The distribution of the data is multivariate normal. If we have capital I items, it's an I-dimensional multivariate normal distribution, where the mean is set to be equal to the vector of intercepts plus the matrix of factor loadings times the matrix of factor scores. And the covariance matrix is usually a diagonal matrix where the diagonal elements are each of the unique variances. Right? It can in CFA be not diagonal. We can have residual correlations to it. When I teach this from a measurement perspective, the idea of the residual correlation is a weakening of the idea of conditional independence. And to me, that is a weakening of the argument that your factor actually underlies the data. I like to say it's not just the factor that causing the correlation between your items, it's the factor and other things. That's really what it says. Got it? Okay. So next, we need to look at the distribution of the factor. Well, often we call this multivariate normal. And a lot of times the distribution of the factor we have to fix, right? So a lot of times the mean vector is simply a vector of zeros, and the covariance matrix may be a correlation matrix, meaning the diagonal is one and all the off-diagonal terms are estimated. But that can change, right? We can use a marker item and estimate the diagonal of the covariance matrix, right? That's for loading. We do the same thing, put a constraint on one or more of the item intercepts, and we can estimate a vector of factor means. But each of those terms that we estimate are subject to which item we chose to put a restriction on, and will be different given different items, even if they're perfectly correlated with how we do it differently. The example I gave with Erica and I deciding a different identification scheme. Sorry, Erica, I'm picking on you today. But all right. So putting this all together, this is what we have. For the distribution of y, we have to think about what our model implies our data should look like, right? And so here, once we know the factor mean vector itself, we know the expected value for each item is equal to each item's intercept, plus if the factor mean's non-zero, some weighted version of that factor mean itself. Most of the time, our factor means are zero, so that's gone. Okay? The distribution of the variance covariance matrix turns out to be lambda phi lambda transpose plus psi. If any of you is looking for another tattoo, that would be a good one. If you're in this field, just stick it right there. And that way you can gain entrance to almost any club in psychometrics you'd like to go into just by that. No, it's a classic result, right? This is the model implied covariance matrix in CFA. You see this in a lot of places, right? Okay. So you know the distribution. It's funny about this. Like every class I teach always boils down to joint conditional and marginal distributions. And here we go again, right? You've seen this throughout the class. We started talking about conditional distributions and marginal distributions under the idea for factoring a joint distribution because the joint distributions may not be parameterized or easy to get to. And so we can do the same thing here. We use this result here to say that the distribution, the numerator in Bayes' theorem, is the distribution of the data given the factor times the distribution of the factor. And using the reverse logic of our factorization, right? If we multiply by x and divide by that, we can end up saying that what we end up getting here, actually, sorry, multiply by f of x on either side, the joint distribution is f of z given x times f of x. This is just another way of saying the joint distribution, the numerator in Bayes' theorem is simply the joint distribution of our data and our factors, even though we never observed the factors in the first place. With me so far? Okay. Then there's this multivariate normal thing. In the multivariate normal distribution, we in CFA assumed all of our items were normal and all of our factors were normal. Sorry, all of our items are normal through the assumption of normality of our error terms, our residual terms, right? So I'm working towards something here. So we can show that this joint distribution is also multivariate normal, even though we didn't observe the factors. And then we can use that result and the features of the multivariate normal to actually come up with what the factor score distribution should be in CFA, a closed form result for it. Right? This only applies for measurement models assuming multivariate normality, and IRT, it doesn't really hold, but it becomes asymptotically normal as you go further. This result doesn't work, but here's part of it. The multivariate normal, I didn't dive headlong into in this class. When I teach multivariate statistics, it's basically make friends with the multivariate normal, but it has some really sweet properties. Sweet, awesome. Like that, the sort of all of statistics was founded on up until like the 1970s, right? It's pretty amazing. That means that conditional distributions of sets of variables, or the conditional distributions of sets from variables from a multivariate normal distribution is also multivariate normal. So think of it this way. If I had a big data matrix X, and I partitioned it so that the first Q variables were X1 and the next P minus Q variables were X2, then I would be able to partition the mean vector similarly to have a mu1 and mu2, a mean for the first group, a mean for the second. And there would be 4 different quadrants of my covariance matrix, right? The covariance matrix of just the first set of variables, the covariance matrix of just the second set of variables. And the off diagonal, it's sort of the covariance of one set with the other, but these are transposes of each other, right? Okay. Under multivariate normal, go to Wikipedia and find this slide, all right? The distribution of the first set of variables conditional on the second follows a normal distribution where the mean is given as a function of those partition matrices, right? Mean vector 1, all this other stuff. And then the covariance matrix is the same, right? And of note here, the mean vector does depend on the actual scores for those variables that are not there, right? This is basically a multivariate regression model right here. And these matrices provide some of those parameters in the multivariate regression itself. Okay? So we can use that and quit calling this X and whatever, and we can plug in Y and F, right? So here, really, if we think of this as a joint distribution of our data and our factor scores, if we partition the data from the factor scores, we know the mean, we know the covariance matrix, we know each of these things. I didn't show you that the off diagonal will be lambda times phi. That's lambda is the matrix of factor loadings, phi is the covariance matrix for factors. And then using each one of these partition quantities, we would be able to describe the factor score mean, which is that thing, and the covariance matrix, which is that thing. And every time I was in structural equation modeling, anyone ever looked at David Kaplan's book? David Kaplan, professor at Wisconsin. Pretty nice guy, like him, like his work, endorse. Like if you start to see certain quantities in SEM, you start to just see this. It's like matrices piled upon matrices piled upon matrices. Like yeah, clearly this is it. Well, this came from all of the theory of multivariate normal. And once you start chunking it into sections and so forth, you will see why you have to put each piece in a different place. But what that means is the factor score itself, the mean of it, is sort of a weighted regression. It depends on our observed scores, item responses, minus the mean for each item. So they're sort of centralized, right? And then rescaled based on factor loadings, factor unique variances, and so forth, right? So I think it's kind of cool personally. Once I learned that, I was like, oh, that's why all the matrices show up. And also when I made this slide, Levon was somewhat younger. I was thinking 2015, and they didn't have a way of making scores for CFA. So I was like, oh, well, I need to make scores for this. So I just got the matrices and built those. So never know when you're going to need it. Point I'm trying to make though is this is all this math means for factor scores is that they're multivariate normal. They come from a, we know what the mean it should be. We know what the variance should be, and MAP and EAP are the same. Now I'm going to link factor scores to classical test theory now. Any questions on that? Gosh, I should just ask for questions. Just like don't ask questions. Just let me give you my strong opinions. All right. God, I'm terrible today. My apologies. Um, some scores, adding items up, have a correlation of 1 with factor scores from a parallel item CFA model. That doesn't matter if your data are binary, Likert, or otherwise, right? So in a parallel factor model, all factor loadings, all unique variances are equal. So here's a parallel items model. I accidentally made a mistake on the means. These means can be different. One loading, one unique variance. Okay. I'm going to, with a common loading estimated though, right? This is a constraint. We could estimate the factor variance, but I'm not going to. I'm just going to estimate it to be 1, set it to be 1. And when I do that, this is what I get. The graph here on the bottom right, on the x-axis is the factor score. On the y-axis is the sum score. That thing's perfect. This is the picture where everybody was, like, this is the slide everybody's taking pictures of at the conference. I was like, y'all don't know this. We got to talk about this better. We don't do a good job in doing this. You don't hear about this in theory and technique, but it's there. Factor scores are parallel item scores. All right, right there. Okay. So, any debate with that? Argue with me. Just kidding. I'm in a feisty mood today. Actually, I'm not. I don't want to fight. But and you can take a look, for each value. But before we get too far, because here's the thing: when you put the sum score on the factor score idea, what we can do is start looking at model fit. So here we have it. Our parallel items model for 3 items gives me an RMSEA. So if you do not use parallel items with 3 items, it's just identified, meaning model fit looks perfect. 0 RMSEA and 1 for CFI TLI, right? Here, our RMSEA is either 0.92 and their ML or robust ML 0.053. Maybe fit, maybe not. Arguments could be made as to whether it fits, depending on which journal you're publishing it, right? We could also talk about factor score reliability, like we can get an estimate of that. And so for us here, our reliability is 0.73, right? So not great, but we only have 3 items. So now we could actually do classical test theory from a CFA perspective to understand reliability in that sense. This was the thing I learned from Rod McDonald when I was, again, in his class. Again, in classical test theory, we have our true score plus error formula. In CFA, the unit of analysis is the item. And so if we put those two together, we'd say the total score for a given person, the sum score, is just the sum of the items, right? So then, if we map the sum of the items onto the CFA model, right, we get the sum of our CFA model for each of those items. And then we can sort of distribute this sum and see we get the sum of our item intercepts plus the sum of the factor loadings times the factor score plus the sum of the error terms. So if we map this onto classical test theory, the true score portion of that is like the model for the means part. And the error portion of that is the sum of the errors. And so then we can talk about variance for each of these terms from a statistical point of view. The variance of the true score is the variance of the sum of these mu's plus the variance of, well, remember, a constant times a variance, a constant squared comes out, right? That thing times the factor score. And so now, with the variance of all this, variance of a constant goes away. What we're left is the sum of the factor loading squared times the factor variance is the variance of true score, if we believe the CFA model exists, and we're summing up items, okay? The variance of error is simply the sum of these error terms. Now, this is if there's no correlated residuals. If we have correlated residuals, we have to add 2 times their value to this term, okay? And what you're going to see is the correlated residuals actually reduce reliability for your estimate of the sum score, right? It's basically you can think of a correlated residual as an indication of non-unidimensionality or doesn't fit the dimensionality of your model, and that should reduce the reliability. Your precision should go down. So now, if we put that back into the previous reliability formula, our reliability can be expressed solely as a function of CFA model parameters. And we do this in Lavaan, and we get an estimated reliability of 0.629 and a standard error of 0.025. We can actually get an error on reliability from this process as well. So we now have 2 reliabilities. We have the reliability for the factor score, which is 0.73. And now we have a reliability for what? The sum score. That's right. So under a sum score, your reliability is 0.629. This is different from the factor. And in part, why it's different from the factor has nothing to do with the model as much as it has something to do with our prior distribution for the factor. Our prior distribution shrinks variability in the factor, which makes it look like it has more information. The more items we have, the impact of that prior distribution will be limited. We only have 3 items here, so we don't expect a whole lot. So how are we doing? Okay. So that estimate on the parallel items model, that's a Spearman-Brown reliability. And if you want to go try it out, you can go take the data and compute Spearman-Brown on your own with however you learn how to do that. It will be that number. You just won't have a standard error of your method, most likely. Right. There are other CFA models, right? The tau equivalent model allows us to have different error variances with the same factor loading. Again, we could test whether tau equivalency works or holds with the model fit. And here, this is an interesting part. When we go and put tau equivalent model, what we end up getting here is this is the factor score on the x-axis. This is the sum score on the y-axis. And this is the part where I was talking about, right? Take a look at the value of a sum score of, let's say, 10. Right? If we use a sum score, everybody at 10 is equal, and they're less than 11. If we use a factor score, there are some people who are higher with a 10 than they are with an 11. Similarly, they are lower than a 9 for some people. And that's the difference between parallel items and not. Your ordering of people changes. In fact, if the model fits is even worse, you'll see a bigger change in all this. So which one should you use? Which model fits better? Factor score model. So, there we go. Yeah. So these are the factor scores under the parallel items model and under the tau equivalent model. They're not a whole lot different. Here's one that is about 10.1 away, but they can be quite different. So this is the difference comparing these. The other point I wanted to make is reliability is not a measure of model fit. You can finally also have the unrestricted model itself. Some people call this the congeneric model. I hate that word congeneric. I don't know what that means. Help me out with English here. Anybody? Generic versus congeneric. We put a prefix on that's con. Anti-generic, maybe? I don't know. Whatever. So this is where all parameters, loadings, and unique variances are estimated. That same formula still holds. And so the reliability, or sort of check that. If we look at our model fit for each of these, we can actually use a likelihood ratio test. The likelihood ratio test still prefers the most complex model. So the model that would fit, we'd sort of reject classical test theory with it. And again, you see the same thing. Now, it's a high correlation between these scores, 0.997 and otherwise. But that correlation will go down if the model fits is poor. Actually, model fit being the biggest thing here. Anyway, so I could go on and on and on and on and on, but I'm going to stop there and talk a little bit more about that. So up to this point, we've seen the assumptions underlying sum scores. So the sum score I'm trying to make an argument for is that you need to impute it values for it too, if you use it in the secondary analysis. So how would you do that? Right? If you said, let's imagine, because it would never be you because you took this class, right? But let's imagine your advisor said, I'm going to use a sum score in a secondary analysis. And you're like, wait, I took this class, and yeah, I know nobody likes Jonathan Templin, but he's got a point. You gotta admit, I got a point, right? Science suggests I have a point. Right? What would you do here? How would you generate plausible values for a sum score? You'd have to come up with some type of idea for what the distribution around the score happened to be, and then generate random values based on its error, right? And what we can tell in the classical model, in this version of the classical model, in the parallel items model, there's all sorts of models for classical tests, right? Like you can get to like 4-parameter Bader model if you want as well too, which is a little bit different because that's conditional standard errors. But basically, each one of these scores has the same standard error, right? It's unconditional. It happens to be 1 minus reliability times your total variance, right? So if you assumed that the true score itself had some normal distribution because you had enough items, because things go normal, then you could take that normal distribution, center it at the point estimate of the true score or the sum score, and then its standard error would be the standard error of measurement around it, and draw values from a normal distribution from it. So then you could have plausible values for all your test scores, even though you observe the test score itself, right? So like a person with 10 will have values that'll be bigger or less than 10. But that's what the idea of imputation needs to be. And so doing that is guarding against unreliability in your measurement quantity. That's how that would work. Yeah, that is what you have to assume, yes. Yep. But if you do, then you sample from a normal distribution around the sum score itself. Yes. All right. So the point of this lecture, I'll just highlight that, is that if you're ever reporting scores but not using them in subsequent analysis, use a factor score. But what we haven't seen is what to do when we cannot use a simultaneous analysis or SEM, and I'm going to show that in the next lecture, which is right now. Secondary analyses with scores. There, I put it together. These were separate before. And yes, I was lazy and I didn't read all my slides. My apologies. Okay. So I'm going to take another example to introduce and motivate SEM. This is a data set where we had 150 simulated participants who provided self-reports on a happiness scale and their marital status. I don't know why I picked this as an example. I'm not trying to bag on marriage, so don't tell Lisa Hoffman I'm riffing on marriage, all right? There's all sorts of stuff here. But we all can admit that happiness is not about marriage, but this is how this is. Right? Happiness is derived from within, right? I don't know. Now I'm giving you lessons in philosophy that I'm not trained in. So happiness is psychometrics. Happiness is a factor score. We all know that. Am I right? Can I just say that? There, get myself out of trouble. Okay. Participants responded in one survey. There was a 5-item happiness survey, and then a 1-item, are you married, yes or no? and researchers were interested in the effects of marital status on happiness. I know that there's also lots of moderators here, so ignore this very, very simple example. Okay. Um, the variables are measured with error represented as the latent constructs. Right. This is happiness. There's 5 items. This is kind of a path diagram of it. And then you have maybe a marital status here. Right. This is the measurement model, which is CFA, and then the structural model, which is predicting the happiness latent variable itself. That makes sense? So unlike, well, I don't have an example of that. Never mind. This is one where our outcome is actually the latent variable. It's not the opposite direction. And I say that because if this arrow had an arrow pointing the opposite direction, first of all, it's an equivalent model. But the meaning of that is that marital status is an indicator of happiness, not a predictor of it. It's an odd, this is one of the odd parts about these simultaneous equations. So here are all the equations that are implied by that path diagram. Yes. Yes. That would be, you're right. Pardon me. Yes. Yes. Correct. Um, if this were not binary, it would be the same. It will fit, it'll be approximately equal. It's, you have to condition on the link, you have to worry about the link function transformation, but it's within the, like, if you're in the link function scale, it should be equivalent, but that's harder to think about because we don't think about link function and so forth. Under Craig Ender's love of the continuous underlying variable, they're equivalents. Okay? And I say that. I love those too. Don't get me wrong. That algorithm has saved me lots of time. The Albert and Chib algorithm has saved me a ton of time. But that's me, not you, right? So the SEM analysis here is ideal, right? This is when I talk about this is the parallel to maximum likelihood in missing data because we have our quantity here. It's not really being estimated, but we're building this big likelihood function with it involved in it. And we have all the variables that would contribute to that quantity simultaneously in the model itself, right? Wouldn't you know, though, the flip of that is not, there are some other ramifications to this from a measurement perspective, right? What do I mean by that? If you estimate this model with just happiness and you compare it to this full model, these parameters might change values in the full model when it's not here. That's, I don't know how you think about that, but for me, that gives me all sorts of pause. What does that mean? It means, right, we think that these 5 items indicate happiness, and that should be it. But now we're going to predict happiness with this marital status something or other, and it's going to change how these other things relate to happiness? Does that sit well with you? Shouldn't, but that's what happens. So I'm going to put that caveat to you because in a latent variable model, happiness doesn't exist. It's a proxy, right? And it depends on the model. Under perfectly fit, if this model fit perfectly, you might find, like if this bottom part here, the measurement model fit perfectly, you might find predicting it would change these very little, if at all, right? But part of it is model fit, part of it is the optimization process. And so conceptually, to do just straight, oh, I'm going to throw it all in maximum likelihood, suffers from some issues because now you're sort of redefining what your trait is by other parameters that are not involved in the measurement of that trait directly. And to me, that's somewhat problematic. Does it bother you? Right? Yeah, happiness over here, and I've got 5 items that are supposed to measure it. It shouldn't matter if I predict it with marital status or whether I just won the lottery or whether or not I woke up and just felt good today, right? Something along those lines, right? That shouldn't change how these 5 variables relate to happiness, but it will. So I say that to you because this may be the maximum likelihood version of what we would be doing in our missing data class. And that's good. However, the measurement model itself will change because of it. And that's not so good to me. It has implications for validity. It has implications for how happiness is related to things. And so I say that because what I'm about to show you, the plausible value technique afterwards, doesn't have to have the simultaneous approach, where you can break this into two stages if you build it from the missing data principle of trying to fill in what happiness might have been under just the measurement model. Yeah. It is not always the case, but it's more common than you realize. And it's an interesting phenomenon. It's one of the things in psychometrics that just drives me. There's a theoretical property of how things work that drives personally me nuts. It's kind of like saying the same thing about should you use a prior distribution for your latent variable if you have a high stakes assessment, right? Or a multidimensional IRT model, because now that prior is not necessarily, it doesn't reflect individuals and reflects a group, but our score should be individual based. These are things that are sort of incongruencies. I don't know if that's the right word. Things that are sort of just a mismatch of what we really believe is happening versus what's happening. So what I'm saying is there's more reasons than just choosing ML as a gold standard to not use this simultaneous approach itself, right? And one of that is this allows you to estimate the measurement model itself and then estimate a secondary model on it that doesn't change the measurement itself. Happiness is defined by the measurement model. Then you go and do plausible values for happiness and use that in the secondary analysis itself. Does that help? Yeah. Hmm. That's right. Yeah, it does. And it's, how do you like that? It's surprising, right? Now, it may not change by much. And I think what we're talking about here is more a model fit issue, but it does change. So, or it can change. All right. These are the equations implied there, right? So basically, each item is the CFA model, and then happiness itself has some intercept plus some slope or some difference or change in factor mean for the marital status plus some error. Um, I say the SCM analysis is often thought of as the ideal. I'll go with that, with the caveat I just mentioned just a moment ago that it's not always ideal. It may be somewhat less than ideal. It's ideal from the missing data perspective, the simultaneous analysis, right? Um, and here's the results that we end up having. Our model fit RMSEA is 0. Looks good to me, right? Here's our estimate of our happiness unmarried. This is, I don't have the intercept for it here. This is the slope, but married people have a higher factor mean by 0.567, but hey, it's not significant, so don't just rush off and get married, all right? Okay? Okay. Sorry. I feel like I'm really skating, like gonna get myself in trouble. Someone's texting Lisa Hoffman right now. He's ripping on marriage. What's going on at home? It's fine. It's fine. It happens. Um, now, we could do the same analysis with a sum score. That's a secondary analysis, right? So what that would look like is if we took happiness and just added all those 5 variables together and just had a regression, right? Could do that. And when we do that, our estimate's now 1.07, and that p-value is now significant. So guess what? What I just said about the latent variable approach that don't just run off to be married, if you use a sum score, you should go get married to be happiness, all right? And again, I'm not actually pitching that, but I'm using this example to sort of drive the point, which is marital decisions should not be based on sum scores versus CFA. We all know that. But second, um, this is a very different result for something that's supposed to be the same construct. And at that, let's pause for 10 minutes because I need more water and I'll be back. Thank you. All right. So, yes, what we just saw was using a sum score gave a really different. Here, let me see if I can. Oh, no, hold on. It's not here anymore. Never mind. All right. This number here, 1.077, was quite different from 0.056. But there's actually two reasons it's different in this example. One is we didn't use the simultaneous approach. Two is that this is a parallel items model, and the previous model was congeneric, where each loading was estimated. So why it's different, you can't just necessarily pin on, oh, it's missing data, oh, it's not doing the right approach. This is a little bit more complicated than that. You have to sort of disentangle both. But it's different, and it's widely different. And why I showed this example is because this is what most people would do, including myself. Let's just say, hi, my name is Jonathan, and I've put some scores in analyses before, right? Some score users anonymous, should we just call that? No, never mind. Another bad joke. I'm going to get in trouble today. First, marital happiness. Now, anyway. All right, now we could do a factor score as well, too. Right, so we could do the same. This is just the CFA model with happiness in it. And then we output the happiness factor score itself here. Checking model fit, good fit. And then the factor score analysis example is where we take a look here. That value is now 0.23, and it's, just a little bit more than significant. But that's using the point estimate of the factor score, not a missing data approach. So this analysis, this number, now what are we doing here? We have the congeneric model for the factor analysis, where every loading and every unique variance is estimated. So, and then we output a factor, the EAP estimate, or MAP, it's CFA, so it's the same factor score. And then we stick that into a regression model, and we get that estimate. So the only difference between this, there's sort of two differences between this and simultaneous. One is the parameters themselves, the actual values have changed a bit. Let's take a look. 0.2, 0.04, 0.21, 0.22, 0.74, 0.27, 0.09, 0.26, 0.23, 0.058. These numbers have changed, right? The thing I was telling you about. So it's not entirely comparing the same numbers in the same system, because the factor score that we created under just the factor score model was not simultaneous to the prediction of the factor, which changed the factor definition. So that causes a bit of a problem as well, too. But here are our standardized estimates and our standard errors. And you can see one other big thing here is the standard error under the simultaneous approach is much larger than the standard error under either the sum score and the factor score. Now, that is a missing data thing. That's because we took a 5-item survey. I don't think I calculated what the reliability for the factor score or the sum score was. But we took that survey and we just summarized it with one number. And so we think we have a lot more information about the trait than we really do, and that's showing up in the standard errors themselves too. So not only do we have a biased point estimate, we also have a biased version of the standard error as well. So I'm hoping to make the case why this fits in the missing data. Does this seem familiar to you from a missing data perspective? Right? So how would we do this a little bit better, right? So this is the plausible value part. For secondary analyses, some scores by themselves won't work or work well because they don't provide any mechanism to detect for model misspecification, and they ignore the presence of measurement error, right? And again, I keep saying model misspecification error is the biggest problem. Right? Why you see people who do a CFA to check unit dimensionality and then output a sum score is to check the unit dimensionality at least, even though the sum score should really do a parallel items version of it, right? Factor scores by themselves don't work because they ignore measurement error also, meaning we don't have the error in the factor score. Now, it's nice, the factor score, we can at least get good model fit. So model misspecification error is reduced, but we still have the issue with us truncating a variable that has a standard deviation that's bigger than 0. Basically saying, you know that distribution of factors scores? Forget it. We're just use the point estimate as if it were perfectly measured, right? which we know statistically is one of the problems with missing data, the thing I was saying. That's single imputation. I'll just put it that way. Using a sum score in an analysis is a single imputation method. Using a factor score in an analysis is a single imputation method. And I may call these factor scores, but those of you who are doing this with IRT, this is you right here, right? How many of you have outputted a theta and done another analysis with it? I bet you've done it in which area? Uh, Old versions of model fit, Q3, X2, anything before the Thyssen or Orlando work, 2004. Almost always use outputted scores. You probably used it to look at item characteristic curves a bit. I've seen that before. Have you used it in equating? Ooh, there's the question I thought of today. I want to know the impact of missing data on equating. Ask that question, right? Where else have you used an outputted theta before? Anybody else? Any other methods? Yeah, CAT, MST, all of that. Single imputation. You put it that way, it sounds pretty bad, doesn't it? At least to me. This class was all about, hey, single imputation is bad, okay? Don't do single imputation. We at least all agreed on that. Fixing it, not easy, but that's it. So I'm saying that. So look, I've done it too, all right? So if you've done it, I'm raising my hand. I'm not here to tell you you're a terrible human being for doing it. We all have to do it sometimes. But just have that voice in the back of your head. Saying, hey, you took a class about this. Should I be worried about that? Right. And then go on. Don't mention it to your advisor because they won't want to hear it. But when you build your company or when you build your example or when you go and work somewhere and you have a say in it, then remember it because that changes a whole lot. Like I sit on a technical advisory committee, state of Missouri, uh, and those of you in my multidimensional class, multidimensional measurement models class, remember the exercise where we had to go and look up state assessment uh, technical manuals, and we sort of applied psychometric principles to each. So the vendor is presenting technical stuff, technical advisory, the technical manual for whatever method, and I'm like, almost all of it's built off of this method, right? And so there's a big debate in my head, which is why do vendors get to charge for the pleasure of assessing people but not keep up to current methodology? And no one can answer that satisfied to me apart from, oh, well, the state doesn't ask for it. Well, who advises the state? Well, technical advisory committee. How many members of that ask for it? Well, I do now. Right? I won't tell you the details about what goes into it. But I argue that this actually hurts us as a field in the science. And in talking to the vendor, I was saying, we train our students on modern methods. And like, yeah, and then we get your students have to untrain them and teach them the old stuff. Like, who's in the wrong here, right? So when you get to be in that situation, do me a favor, hit me up. I'm happy to show you the scars I've got. But at the same time, it does matter. It does change things. It does change things a bit. So anyway, factor scores are less prone to model specification error, but we can't just use one factor score. So what I'm getting toward is the multiple imputation strategy. What we'll do is treat factor scores as missing data and multiply impute what are called plausible values for these multiple analyses with factor scores. This is the Mislevi, Johnson, and Meraki paper that really talks about scaling procedures in NAEP. NAEP is the National Assessment of Educational Progress. Have any of you ever done a NAEP data training before? I don't know what the federal government will do with NAEP. I hear it's still around. But back in the day, NAEP would have a data training seminar, and you would apply, I think it was in part through Institute of Education Sciences, also funded through NSF. You could apply, and you would be basically paid a bit to go to Washington, D.C., and to learn how to use NAEP data. And NAEP data, part of the training, was we don't just give you for each person. The NAEP assessment itself has this interesting spiral sample design. And so if you want to look at, let's say, fifth grade math score, or I guess eighth grade math scores is fourth, eighth, and 12th grade is really what they assess. If you wanted to look at them, you wouldn't just get one theta, they'd give you five. And much of the training was built around what do you do with those five scores and how do you do what we know in this class to be estimation and pooling. in that case, they actually use a little bit different method. Um, it's essentially equivalent depending on which where you look at it, but it's sort of a simultaneous analysis with replicate weights. But okay, so this is what I'm really trying to tell you from a um, so dealing with missing data is important. This is bad waste. Um, so this is what we've seen before. Single imputation's bad, right? Anyway, multiple imputation is what we try to do. You saw the multiple imputation phases. The distribution is the key. And the nice thing about the factor score is we most likely know its distribution, right? Now it's approximate, right? But the posterior distribution of the factor is what we can draw factor scores from. We can do so using plausible values and so forth. Let's see here. Here we go. Let's just do that. So what do I mean? We know the distribution of the factor. The distribution of the factor given the data, even though this is terrible math, is this. Yes, this is not. I'm not advising you to put this on your body like tattoo wise, although there's that core, that part right there. That's the tattoo, right? Um, or better yet, this hashtag right there. Just go on to uh, I would recommend Blue Sky, but if you have to go with well, I'm never going to call it X, Twitter, it'll work there too. Hit me up. It's good. Um, Here's me doing this by hand. You could now there's now built-in functions in Lavaan. I think lav predict the predict function works this way. But basically, what we can do is take our factor loadings, unique variances, item intercepts, factor variance, and factor mean, create our overall covariance matrix, our data matrix, and then get our mean of our factor scores and our variance for each. Right. So this right here, this scores object right here has everybody's factor score mean. The variance of scores is each person's variance of their factor score. And then what we could do is literally loop through for each imputation and sample for each person from a normal distribution. So here I'm actually doing a little bit backwards, but I take the error and I basically transform it to be mean of scores on this other the variance of the standard deviation for the sum score itself. So now what we end up having for each person is a set of imputed values for their factor score. Looks like this, right? This black line is the density. Sorry. This is our imputation. We have 1,000 imputation values. This, by the way, is not, how do we want to call this? Is this a Markov chain? Yes, but no, because I'm drawing from the same distribution independently at each point, right? So if the autocorrelation is here, it's not because of the process. Like iteration 2 does not depend on iteration 1. We always have the same mean vector. It's just drawing from a normal distribution. You can see as the number of imputed values goes up, this becomes, the black line is our density from the imputation process. The dashed red line is what it should have been. So we have this nice approximation. And take a look at, by the way, this observation 1's factor score. Observation 1 had a score of 0.75. Look at the values we're imputing for that, right? That's a heck of a range. And that's the thing I'm trying to underscore. Ed measurement data or psychometric data has a ton of error in it for normal amounts of items. A ton, right? Pretty amazing. So then what we can do is go through the pooling phase. So what do? We could actually come up with, for each, we could do for every factor score, create a brand new complete data set and do the simultaneous analysis over and over and over again. We've seen the pooling work before. This is the pooling math that we saw before. I actually did this with the run mi function here, which is a built-in to SEM tools. SEM tools is the package that became lavaan.mi, which I showed you to use in the multiple imputation part. Some of the former students at Kansas work with Todd Little built that. It's kind of useful. And when we do that, now we get the following information. Um, we run all this, we pull it together, we get an estimate of 0.237 and a standard error of 0.197. Didn't change a whole lot, but did values. And so here we can see this again too. The factor score imputation had a even smaller estimate for the standardized effect and a similar um, standard error to the other two methods. And you're just thinking, wait a minute, why is the standard error about the same? Well, part of that is the specification of the model itself is a bit different, so that estimation error shows up in the simultaneous SCM a little bit more. But again, we're back to believing that marital status is not dependent on, or happiness is not dependent on, marital status is not a predictor of happiness. There we go. So how are we doing? How's that? How's that sit with you? Yeah. Yes, that's right. Yeah. Because I was being difficult, I could have done it this way. Scores itself as a constant. So take a look here. This thing right here is a normal, standard normal, right? When we add a constant to it, that really should be its mean. So the mean should be scores. And when we multiply that by a constant, that changes its standard deviation, right? It becomes the standard deviation of the basically the standard deviation is the square root of what this happens to be. So I could have done this all on one line. I didn't. I think when I coded this, I was confused as to whether or not R would give me a unique value for all of the means. It will. I know R better now, but this is old R code. Sorry about that. Yeah, that's right. So the actual score is the MAP or EAP estimated score. The actual standard deviation should be the standard deviation as well of the score. So think of it this way. Score, if you're in classical test theory, that would be the sum score. In classical test theory, this thing would be the standard error of measurement. Okay? If you're in CFA, score is your EAP or MAP estimated factor score. We don't use those labels because they're the same. And this is the standard error of the factor score. If you're an IRT, this will be the point estimate, the EAP estimate or MAP estimate of your test score. This will vary by person. That's the conditional standard error, but it still can be done. Those are the three big paradigms you tend to see. Anywhere else after that will follow what IRT does, is that somehow you'll get a score and a standard error for that score, and you can still do the same process. Does that help? Yep, you're welcome. Okay. All right. So that is it. That is basically things to think about. It's a poor example. It's not as fleshed out as I probably should have done. But I was hoping with this to give you the idea of really keeping error in your analysis when you do a secondary analysis, right? If you don't acknowledge that factor scores or latent variable estimates or sum scores have this distribution to it, your secondary analyses will have potential biases to them, right? The remedy for that, this is a very obtuse way of doing it. Um, if you're working in a testing program, you can automate most of it under the context of your program in easier ways than this. Right? There may even be built-in functions already. M plus does a good job with this. I think they have a plausible values estimate. I was playing around with MERT today to try to give an example. It didn't actually succeed in it because MERT gave me output I wasn't expecting and wasn't doing what I was expecting. So I don't know what I've done wrong, and I couldn't fix it in time. But MERT does have an F scores function where you can output the factor scores, and an option in that is plausible. Right? So if you choose in MERT, if you're using IRT and you use the MERT package in R, F scores to get your theta estimates. It defaults to EAP estimates, but you can change the method to plausible. and it will give you a sample of estimates for each person, right? So that is what I recommend trying to do. Um, so there are other ways to reduce error. All right. Secondary analyses are tough because they're not the gold standard in many places. But I mentioned to you today that secondary analyses and psychometrics may actually be better from a validity argument point of view, because your secondary analysis preserves the validity argument and the statistical validity of your thing you're trying to measure. Whereas in a simultaneous analysis, the model parameters change, right? Things change potentially, and they may change a lot. So secondary analyses, I think at the time when I made these slides, my thinking was, yeah, these are not the gold standard. I think I'm okay with secondary analyses now for a number of reasons. Um, we just have to do them in a way that sort of reflects the missing data ideas, that we can't just plug in single impute scores in how we do things. So for each source of error in a secondary analysis, there are ways to reduce that error so that the secondary analyses are able to be computed with a good degree of accuracy, right? Some of these ways are very difficult, if not impossible, with these current methods. That's a research topic if anybody want to look at that. But some are very possible. But all of the slides assume that no sum score analysis is used. These are all factor score analyses based with imputation. Okay. So how do we reduce measurement error? Right. This is of the measurement model. You know this already from your psychometrics classes, or you should think about it. You need to have a larger number of high quality and highly informative items measuring each factor. Right. In some contexts, that could be done with a computerized adaptive assessment, to a lesser extent, a multi-stage test, right? And not all methods are created equal. Not all items are created equal. How do you know which ones are good? Well, if you're developing an instrument, that's the process. It's hard. I think developing an instrument for cognitive skills, like an educational measurement, is hard. But I'd say doing so for a psychological construct such as happiness might even be harder, much harder, because we can all sort of agree what, let's say, the standard for NBT1 happens to be, numbers in base 10. How do we measure if a student knows numbers base 10 at the fourth grade level? Well, we have a definition of that that's fairly narrow, and it's mathematical, so it's fairly logical. So I say, let's measure happiness, and I create 5 happiness items. I'm pretty sure your items might be different than mine, right? One of my items would be like the San Francisco 49ers win the Super Bowl. All right? Niners? No. Never mind. Anybody a Niner fan? Extra credit. I'm just kidding. No. Point being, constructs are made by definition, and in a lot of work, particularly in personality theory, all the way to education measurement, is defining what that definition needs to be, and it's constantly in flux. Anyway, but the ramifications, measurement error is great to reduce. We want highly reliable, accurate measures of people's values of the construct or the scale or the ability that we're trying to estimate. And when we reduce this type of error, we have greater reliability for the factor score, greater power in our analyses, and less need for a large number of imputation steps, right? If this factor score distribution was more narrow, we wouldn't have to sample so long to get the tails estimated properly, potentially, right? That's what that means. Additionally, what statistical methods we need? I mean, we just saw that. Multiple imputation of plausible values of factor scores using the factor score distribution from your measurement model only analysis, right? Why the measurement model only analysis again? Because the simultaneous model, the ideal and most missing data, changes the definition of the factor, and that may not be good for you. In some contexts, it'd be okay, particularly in social science work. If you're doing structural equation modeling, people do this all the time. But if you're really trying to understand validity arguments of the factor you're working with, simultaneous is harder. The difficulty in this to reduce measurement error is that the more items you add to a model, the less likely the model fits. So now you're trying to like, I don't know, it's like, what's the old game, whack-a-mole or something like that? You've got measurement error popping up and you hit that one down and model misfit pops up. You try to hit that one down. Like it's like all the time you're trying to do one thing, something that's like squeezing a tube of toothpaste where there's a hole at the bottom of it, right? Like, no, maybe that's not right. I don't know what I'm trying to say, but the point I'm trying to make is um, none of this is really easy in a practical sense. And that's why science is hard and research is hard. Okay. Impact of the prior distribution of factor score. I didn't talk about that much. I'll just skip that. More items is really the answer to that. Sampling error. How do you fix sampling error? Simple. Get a bigger sample. How many of you are collecting your own data? Oh, you're lucky. That's good. Keep it that way. I don't know if you existed in the era when everybody was started talking about like it's like when we finally realized we're putting machine learning and data together. This is like 2010. People would run around saying big data, which made me laugh. Like, why do we have to sound like cavemen saying talking about data? And then the other thing I thought of is all the people I work with who are collecting their own data. To them, everything's big data. It takes a lot of effort and a lot of social science work, right? But yes, if we have a larger sample size, you have better precision for your measurement model parameters. Better precision for your measurement model parameters leads to better estimation of your factor scores, which helps in all the analysis as well too, right? Still want to use multiple imputation with all that. If you have a smaller sample size, guess what? Those of you who took my Bayes psychometric model class, we talked about this a bit. Error in your item parameters is the problem with small sample sizes. Hey, the good news about small sample sizes, power to detect model misfits lower. Looks like your model fits, but you got a lot of error in your parameters, right? Again, the whack-a-mole. Um, if you use MCMC to estimate your factor scores, to estimate your model, those posterior distributions for each person, those are the imputed factor scores already. You got them. You just have to do the pooling and estimation and pooling phases, right? And if you have error in your item parameters from small sampling error, that will show up in wider distribution, posterior distributions for your factors. So this is an argument for MCMC. Bayesian psychometric models might help if you have small sample size. All right. There is actually a bias for using maximum likelihood in this case too. This is the funny thing that in the stat department, people talk about ad nauseum. In psychology or the places where in social science where factor analysis came from, we sort of don't mention it. But in mixed models, those of you in Lisa Hoffman's class, what's your estimator that you use normally? Like LME? L, yeah, or Procmix. REML. Why do you use REML? Right. In factor analysis, same likelihood function, almost the same structure. Do you see REML? Oh. So what do you think about our unique variances? Yeah. Yeah, particularly for smaller sample sizes. So now that doesn't mean you can't create a REML estimator for fact. In fact, you can actually trick Procmix to estimating factor models if you wanted to. But that's what this slide is. If you use maximum likelihood estimates of variance components, they will be biased. And actually, this also happens in Bayes' world too. The model data likelihood in Bayes is multivariate normal, whereas it should be the likelihood that we use in the residual maximum likelihood. We could do that. Actually, try to do a paper on that. I've never finished that paper. Love to. Anybody want to give me some help? Come on by. But Bayes also has a problem with this. So how do we fix it? If you're in the CFA world, good luck. This problem mostly applies only in CFA, though. So if you're in IRT, you're not estimating unique variances. Okay? So it shouldn't be a big deal. And oftentimes in the measurement model, you fix the factor variance, and it's not estimated either. So that's not a big deal. Uh, Impact of model misspecification area. Let's see here. How do we reduce model misspecification error with types dimensionality, constraints, and linear prediction? You got to get good model fit. If you don't have good model fit, game over. So everything in psychometrics revolves around model fit. I always like to say the first step in the quantitative validity argument is model fit, model fit statistics. We don't often talk about that from validity, but that's it. You have a hypothesized model. You built items hypothesizing a structure. Model fits the test of that hypothesis. You reject it, weakens your validity argument. Also weakens all the other point estimates as well. So your factor score distributions are going to be biased if your model fit is bad, right? So if the factor scores you're imputing are biased, guess what happens to the secondary analyses? They're not as good either, right? So it's harder to get model fit. I'd say harder to get model fit in Bayesian. Is it? Or is it just more plentiful? Like, we have a lot of model fit in Bayes. You definitely don't see, like, if you go and run a Poisson, I keep using Poisson as my example, but Poisson factor model in M+, it will not give you RMSEA. It will not give you those. So how would you come up with model fit? I would actually say posterior predictive model checking again, the Bayes idea. You can always do that. So in many ways, posterior predictive model checking may be best for model fit for all of these as well too. But model fit, all of these model misspecification error types rely upon model fit. So model fit is paramount because again, why model fit? No model fit, bad factor score distribution. The end. Cool? All right. How about data distributional assumption error? What am I talking about there? In a factor analysis, we assume the data are normal. And I did a CFA with 3 items that were Likert, which are clearly not normal. In fact, these were heavily skewed toward the bottom end of the scale range. I showed you the sum score distribution, but you can imagine what each item's distribution looked like. That's tough. That factor analysis probably shouldn't have been done. We should probably do an IRT model. The first step in this, I say here, oh, hey, you can test which model fits. There's something called the Vuong test from econometrics that tries to tell you test model fit. I'm not as familiar with it. I would just say this. Pick a measurement model that mirrors the distribution of your data. Its type, whether it's continuous, if it's truly continuous, use normal. If it's truly discrete, use a discrete distribution. I would rather use like a graded response or nominal response model for these data. Because, particularly in the case of CFA, that example I did in the first part of class will far, far greater underestimate the variance of the factor. A normal distribution believes that you can have a score. Think of the Likert scale 1, 2, 3, 4, 5, 6 were the data I had before. The normal distribution says there's every single point in between those are possible. And it builds a model such that those possibilities give you information about the trait. The corresponding categorical data counterpart of that does not. There are 6 categories. The end. Each category has a certain propensity to be selected, and that whole thing relates to the trait in a certain way. The quantification of statistical information in normal versus IRT is very different. So think of it this way. I'm going to draw. I already closed my iPad. So I'll draw on the board. Let's imagine I have theta on the y-axis. And if we have item information for theta on the x-axis. We're all told awesome things about IRT, right? The IRT has this information function such that there may be a point of maximum information for a given theta, and that's the type of item we want to give that person. Now, if you take that same, maybe this comes from a discrete, like a graded response model. If you compare that with what we would get out of treating this data as if they were truly continuous and normal, that's the information function. it's almost always way higher because the normal distribution assumes, because of all those fine grade, a 4 and a 4.01 are different numbers. They can change, but we have a lot more information about the data. Think of it another way. If you have a value that can either be a 0 or a 1, and you have a value that can take infinite numbers, the latter one's got to have more information if you observe like more detail in the data. A 0 and 1's one bit of information, literally, like what we would call in a computer. So when I learned IRT, everybody's like, look, this is the feature of IRT. This is great. We can build computerized adaptive assessments with IRT. By the way, this is a flat information function from CFA. Good luck with this computerized adaptive assessment with CFA. It's not going to work. It will be a fixed form, always, right? But it's like taking lemons and making lemonade. You heard that saying, right? Basically, yeah, there's more, you know, information is conditional on the value of traits. So we can have more items that align with people, but that's way less information than if we were to measure that same item on a continuous scale. Always. Always. So what I mentioned by this is if you're treating your data with a CFA model, when it should be a greater response model, for each item, your item information will be lower, potentially much lower. And we know if you're using ML for estimating your factor scores, right? Test information is the sum of item information, right? And that test information, the 1 over the square root of that gives us standard error. We're summing up a bunch of things right here when they should be right there. Our standard errors are going to look far bigger under the categorical model than they will under the normal model, right? So that's why I'm saying this data distributional assumption error. Now, let me give you another caveat to that. I said this with the CFA model here. But guess what happens under a test score when you have binary items? The model that it is equivalent to is a CFA model with parallel items, which means you often will underestimate the reliability of, or overestimate it, excuse me. Right, so that's why I'm throwing that in. A lot of things to think about here. Factor distributional assumption error, that's harder to do. Like if the factor distribution's off, there's sort of multiple minds on this. I don't know that you will be able to do a different distribution. It's a prior anyway. So, all right, let me before I wrap up, let me ask you questions on anything that I said here. I just wanted this to be a thought-provoking class. So you're thinking, are you bored? Got to be bored. I'm bored. Gosh, try not to sound like I'm bored. I hope I'm enthusiastic enough to make you think I'm not bored. But I'm bored as death. I'm bored to death. I'm just kidding. Just kidding. What do you think? I mean, did this map some of the missing data ideas onto measurement psychometrics? What do you think about that? So again, now you can't convince your advisor. I'm not suggesting that. You can convince reviewer 2 or 3, maybe. Actually, there's no convincing reviewer 2. Reviewer 1's the one you really got to focus on, right? And then as you go in your career and you have a chance to think about this, you have the opportunity to where you're not just doing something because someone told you to. Do think this way as well too. Or if you have the soft skills to try to persuade someone, that would be useful too. All right. So wrapping up, the end of the semester, we're almost out. Anything you do with an estimated test score or a sum score is single imputation. And when we look at it that way, everything you do afterwards likely have some problem with those analyses. And that one small example I showed you, the result completely changed, right? Went from, yes, it's significant to, no, not really significant at all. Which one's right? How would you advocate to say which one's right? How I would say it is which model appears to be most fit the data most accurately. I mentioned there are so many ways, so many things in educational measurement that use single imputation. They're almost too numerous to count. How would our processes look different if we didn't? Well, this idea did lead to more modern versions of model fit, the M2 statistics and otherwise, for instance. And as we progress as a science, so long as it's research being done for the good of research and science, we'll get better at this. You just got to get industry to catch up just a little bit as well too. Um, I think personally, though, if you're doing your own research, you got to get your dissertation done. Of course, you've got to follow what your advisor says. But I think you make a stronger case for your own research if you use these messing data methods themselves. Right? You may have some very noisy results, but I'd rather be um, unconfidently reporting results than confidently wrong. Does that make sense? Like for instance, I have a small business I've had to create because of working here, and whenever we provide scores, like we're not doing ML. We use posterior distributions, and then we use the entire posterior distribution, any subsequent analysis otherwise as well too, for that same reason. It's that we don't want. I'd rather tell people we don't know what a student knows than tell them confidently they know something and they don't. That's sort of my I do less the least amount of harm with it. So, all right, that's it for me. That's it for class. We have one 10-minute meeting with each of you next week. Anybody have questions on any of this? Vladimir. Mhm. Yes. Mhm. So those cases, so if you have a one-dimensional version, that's a Bernoulli variable. Each person will have a probability that they're in one class or another. And so what you could do is impute zeros and ones from a Bernoulli distribution with that probability per person. When you have a more than one, when you have more than one dimension, that Bernoulli distribution has, well, in a DCM case, if there's binary traits, there's 2 to the number of factors you have. Each of those will be one of the classes, and each one of those will have a probability, and then it's a categorical or multinomial distribution. And you can impute that way. Alternatively, and I didn't show this, the weighted data approach that happens in NAEP that is in the article I think I sent, the weights of probability, if you augment your person's outcome that you're trying to predict or be predicted, along with the profile of each class and the probability, you would then put it in that model where this thing is predicted by each of the profile values, and the weight, the replicate weight for each person is that probability. And that does pooling in addition to estimation all in one step. Yeah. Yeah. You're welcome. That, by the way, under the broader sense, falls under a heading of 2 or 3 stage estimation of latent class models. Stuff from some of the people big into that, Vermont, Mutane, and so forth, early 2000s, talk a little bit more about how to handle those data. So, all right. Thank you. Anybody else? Thanks for a great semester. Talk to you during the final. I'm